Mount Kerinci is Indonesia's highest volcano and the tallest peak in Sumatra, standing at 3,805 meters, 12,484 feet, above sea level. Located in Kerinci Seblat National Park in Jambi province, it's one of Indonesia's most active and well-monitored volcanoes. Mount Kerinci is a stratovolcano with a large summit crater approximately 600 meters wide and 200 meters deep. The volcano sits along the Sunda Arc, formed by the subduction of the Indo-Australian plate beneath the Eurasian plate. Its slopes are characterized by steep gradients and are covered with dense tropical rainforest at lower elevations, transitioning to alpine vegetation near the summit. Kerinci has a long history of eruptions, with recorded activity dating back to 1838. The volcano produces primarily explosive eruptions, generating ash columns, pyroclastic flows, and volcanic bombs. Recent significant eruptions occurred in 2009, 2013, and 2016-2017, with the most recent activity producing ash plumes reaching heights of 1 to 4 kilometers above the crater. The Indonesian Center for Volcanology and Geological Hazard Mitigation, CVGHM, continuously monitors Kerinci through seismic stations and thermal cameras. The primary hazards include pyroclastic flows, volcanic ashfall, and lahars during the rainy season. Several villages on the volcano's flanks are at risk, and evacuation zones have been established within a 3-kilometer radius of the summit crater. Despite its volcanic nature, Mount Kerinci supports rich biodiversity within Kerinci Seblat National Park, home to endangered species like Sumatran tigers, elephants, and rhinoceros. The fertile volcanic soils support agriculture, particularly tea plantations and vegetable farming on the lower slopes. Mount Kerinci formed through a complex volcanic evolution spanning hundreds of thousands of years. The current stratovolcano sits atop older volcanic structures, with geological evidence suggesting multiple phases of construction and destruction. The volcano's position along the Great Sumatran Fault System influences its magma composition and eruption patterns, producing andesitic to dacitic magmas that create its characteristic explosive eruptions. The summit crater contains a small lake during certain periods, though this can evaporate during increased volcanic activity. The crater walls show evidence of recent rockfalls and fumaroles activity, with sulfur deposits visible around gas vents. Temperature measurements at fumaroles have recorded readings exceeding 90 degrees Celsius, indicating ongoing magmatic processes beneath the surface. Kerinci's eruptions typically follow a pattern of increasing seismic activity, followed by phreatomagmatic explosions that can last from hours to several days. The 2013 eruption sequence included over 300 explosive events, creating ashfalls that affected air traffic and local agriculture. Eruption columns often reach 2 to 5 kilometers in height, with ash dispersal patterns heavily influenced by monsoon wind directions. The volcano holds deep cultural importance for the Kerinci people, who consider it sacred and call it Gunung Tujuh, Seven Mountain, in local folklore. Traditional beliefs include rituals performed before climbing attempts, and local communities have developed early warning systems based on animal behavior and natural phenomena. The mountain is also central to local legends about the origin of Lake Kerinci and surrounding highlands. Mount Kerinci is a popular trekking destination, typically requiring 2 to 3 days to reach the summit via the Kerinci Tujuh route. The climb passes through multiple ecosystem zones, from lowland rainforest through montane forest to alpine shrubland. Weather conditions can change rapidly, with frequent afternoon thunderstorms and temperatures dropping to near freezing at the summit. Ongoing research focuses on magma chamber dynamics, gas emissions monitoring, and the relationship between tectonic activity and volcanic behavior. Scientists study Kerinci's contribution to regional climate patterns through volcanic ash and gas emissions, particularly sulfur dioxide levels that can affect local air quality and agricultural productivity. Mount Kerinci's magma system is fed by a complex network of chambers at varying depths, estimated between 4 to 8 kilometers below the surface. Petrological studies reveal that the magma undergoes significant fractional crystallization and crustal contamination during ascent, explaining the range from basaltic andesite to dacite compositions. The presence of amphibole and biotite phenocrysts indicates high water content in the magma, contributing to the explosive nature of eruptions. The volcano has produced extensive pyroclastic deposits throughout its history, including thick ignimbrite sheets from large-scale eruptions. Recent eruptions generate scoria, volcanic bombs up to several meters in diameter, and fine ash that can travel hundreds of kilometers. Lahar deposits in surrounding valleys indicate significant post-eruption debris flows, particularly during monsoon seasons when volcanic ash becomes mobilized. Kerinci exhibits distinct seismic signatures before eruptions, including volcano-tectonic earthquakes, long-period events, and harmonic tremor. The 2016-2017 eruption sequence was preceded by months of increased seismic activity, with earthquake swarms indicating magma movement. Deformation studies using GPS and INDONESIA'S satellite data show subtle ground inflation patterns before major eruptions. The volcano hosts an extensive hydrothermal system with numerous hot springs on its flanks, some reaching temperatures of 60 to 80 degrees Celsius. These springs contain elevated concentrations of sulfur, chloride, and carbon dioxide, providing insights into the deep magmatic processes. The hydrothermal activity also creates unique mineral deposits, including sulfur crystals and secondary volcanic minerals. Volcanic ash from Kerinci significantly affects local ecosystems and agriculture. While providing long-term soil fertility through mineral weathering, fresh ash can damage crops and contaminate water sources. The volcano's emissions contribute to regional atmospheric chemistry, with SO2 and CO2 releases affecting local climate patterns and air quality in surrounding provinces. Beyond recorded history, geological evidence suggests major eruptions approximately every 50 to 100 years. Notable historical eruptions include the 1838 event that created significant ashfall in Padang, the 1934 eruption with pyroclastic flows, and the 1999 eruption that prompted evacuations. Each eruption has contributed to understanding the volcano's behavioral patterns and hazard potential. Current volcanic risk models incorporate population density, infrastructure vulnerability, and seasonal weather patterns. Emergency response plans include evacuation routes for over 30,000 people living within the hazard zones. The Indonesian government has invested in early warning systems, including automated seismic monitoring stations that can trigger alerts within minutes of significant activity. Scientists are developing advanced monitoring techniques including drone-based gas measurements, thermal imaging, and artificial intelligence-driven eruption prediction models. Research into Kerinci's role in regional tectonics may help understand broader Sumatran volcanic activity patterns and their relationship to major fault systems. Geophysical studies using seismic tomography reveal that Mount Kerinci sits above a complex crustal structure with varying thickness. The magma storage system appears to consist of multiple interconnected reservoirs at depths of 6 to 12 kilometers, with evidence of magma mixing between mafic and felsic components. This multi-level storage system explains the compositional diversity of erupted materials and the episodic nature of volcanic activity. Detailed analysis of volcanic gases from Kerinci shows high CO2, SO2 ratios compared to other Indonesian volcanoes, suggesting deeper magma degassing processes. Helium isotope studies indicate a significant mantle component in the gas emissions, while carbon isotope signatures suggest interaction with crustal carbonates. These geochemical fingerprints help scientists track magma ascent rates and predict eruption intensity. Historical pyroclastic flows from Kerinci have traveled up to 7 kilometers from the summit, following specific valley systems on the volcano's flanks. Computer modeling of these flows reveals velocities reaching 100 to 150 km per hour and temperatures exceeding 600 degrees Celsius. The 1934 pyroclastic flows left distinctive deposits that geologists use to calibrate hazard models and understand flow behavior in tropical mountainous terrain. Kerinci's ash-rich eruption columns frequently generate volcanic lightning, a phenomenon caused by particle collision and electrification within the eruption plume. Lightning activity correlates with eruption intensity and ash column height, providing researchers with an additional monitoring tool. The electromagnetic signatures of these lightning events can be detected from distances exceeding 200 kilometers. Ice core and sediment core studies from the region show that major Kerinci eruptions have influenced regional climate patterns over millennia. Volcanic ash layers in nearby lake sediments provide a detailed chronology of eruptions extending back 40,000 years. These records suggest that large-scale eruptions may have contributed to regional cooling events and affected monsoon patterns across Southeast Asia. Following eruptions, the vegetation zones on Kerinci's slopes undergo predictable succession patterns. Pioneer species colonize fresh ash deposits within months, while full forest recovery on pyroclastic flow deposits can take 50 to 100 years. Endemic species show remarkable adaptation to volcanic disturbances, with some plants requiring periodic ash deposition for optimal growth. The extensive hydrothermal system associated with Kerinci represents significant geothermal energy potential, with preliminary assessments suggesting capacity for 50 to 100 megawatts of power generation. However, development faces challenges due to the volcano's active status, protected national park designation, and technical difficulties in accessing high-temperature resources in steep terrain. Within the Sumatran volcanic arc, Kerinci exhibits unique characteristics compared to nearby volcanoes like Marapi or Sinabung. Its higher elevation and different crustal setting result in distinct magma evolution processes and eruption styles. Comparative studies help researchers understand regional variations in volcanic behavior along the Sunda Arc subduction zone. Recent technological advances have enhanced Kerinci monitoring through satellite-based thermal anomaly detection, infrasound arrays for explosion detection, and automated gas analyzers. Machine learning algorithms now process continuous seismic data to identify subtle precursory patterns that might escape human observation, potentially extending eruption warning times. Anthropological studies have documented extensive oral traditions among Kerinci communities describing historical eruptions and their impacts. These narratives, some dating back centuries, provide valuable insights into eruption frequencies and local adaptation strategies. Traditional ecological knowledge includes sophisticated understanding of volcanic hazard indicators and seasonal patterns. Thanks for watching. Like and subscribe, and don't forget to explore more geological wonders on our channel.